Okay, so we're going to go ahead and get started at this point.
Yep.
Okay, I think most of you in the room are familiar with the fact that regulations are continually increasing about emissions from the process industry and emissions in general. And so part of the regulations involve measuring what the current emissions are and then reporting these emissions to the authorities. Under some circumstances, instead of having physical analyzers, we are permitted by regulations to use software to estimate what the emissions are. And so that is what we're going to talk about in this presentation. Next slide. Okay, again, I'm Doug White, a consultant with Emerson Automation Solution. My background includes many years in the process industry, and most of that has been in modeling and optimization applications, and then also most particularly assessing the financial impact of these applications. Next slide. Okay, just a bit about Emerson. Emerson's a $14 billion a year corporation. It's been in business for over 100 years. It operates in almost every country in the world, and it is known for an extensive portfolio of automation devices, software, and services. Now, some of the highlights of the last couple of years, one of the highlights of 2022 was Emerson purchased a controlling interest in Aspen Technology. So their very comprehensive and fine suite of software applications now joins the portfolio family of Emerson as well. Sustainability, of course, is at the top of everyone's mind today. And so some of the things that Emerson has been doing in sustainability are down in the bottom left-hand side of the slide. One of the things I did not recognize was that we actually control 60,000 wind turbines right now with Emerson technology. In addition to that, we can control some of the largest solar farms in the world as well, again, with Emerson technology. So you can see some of the other things listed there. You know, about 70% of our sales have some kind of applicability to sustainability technologies. You know, of electric vehicles, Emerson touches the parts in electric vehicles for about 65% of those produced. On the life sciences area, you see it's in use by 24 of the top 25. One of the key things that I think is notable is both of the mRNA vaccines that were developed for COVID. Emerson was controlling the production operation and monitoring the use and monitoring the batches that were produced. So certainly that's a significant contribution in the last couple of years. Next slide, please. Okay, so we're going to talk about what is the problem, then what is the solution, what are the benefits. We'll look at a case study, and then how to get started, and then finish off with a summary and questions. Okay, next, please. Again, environmental regulations are increasing around the world, and certainly we have to be able to meet those regulations in our operations. Most companies, I think probably everyone in that in the room, their company or organization they work for has some kind of emissions reduction program underway. And so to meet the regulations and to meet these programs, we have to be measuring what it is that we are going to be producing. And so we have to measure the emissions and make sure that we report to the regulatory agencies. And, you know, there are sustainability statements that most companies have adopted, and this is part of what they believe is important for attracting talent, and for maintaining their stock price. Next, please. Next, please. So what's the solution? And on to the next slide, please. Well, if we've got to measure what the emissions are, we can use a continuous emissions monitoring system, which is called CEMS. And that typically involves some type of gas sampling, if we're talking about air emissions, of course. And, the sampling system typically is one of the most complicated parts of an online analyzer. Then it's measurement. There's a lot of new measurement technology that is slowly moving from the lab to the field. So certainly there are very good technologies. And then there are that enables us to be able to measure our emissions. But the other option in some cases is to use PEMS, which is predictive emissions monitoring. And with that, we use historical process data and historical emission data to create models, software models, that we then put online, and those models then are fed by real-time process data to produce the predicted emissions. Next slide, please. So in our view, there really are four types of PEMS. First of all, there are what I just showed, which is data-driven models to predict emissions. Then what we call extended PEMS means that if you have a prediction of a real-time exceedance event, to be able to automate the detection or the cause and effect and look at the root cause analysis of what's causing that. And then in terms of optimized PEMS, to be able to add optimization models that provide recommendations on how the plant should operate in the future to, for example, maximize production within emission limits. And then finally, with the structure that we use for PEMS, we can extend this structure to other pieces of equipment in the plant to maximize equipment availability. Next slide, please. So this would typically be applied to items of equipment such as gas turbines, gas engines, boilers, process furnaces, flares. And the sort of things that we're most often trying to estimate will be SOx, sulfur dioxide emissions, NOx, nitrous oxide compounds, methane, CO2, of course, for greenhouse gases, perhaps carbon monoxide. So next slide, please. So there really, in the terms of the online application, there are three components. Now, the first, which is very important, is the sensor validation system. And that, it does us no good to have a model if we have faulty data coming in to base the model on. Certainly that won't give us an accurate prediction. So with modern field devices, they can have self-diagnostics that would enable us to know in the validation system if they are available and if they are working normally. Now, in addition to that, most typically we'll have things such as a range check, a maximum and minimum check on the measurement, a limit check to see if it's within the limits that is desired, and deviation. By that we mean how much has it changed since the last measurement? Now, if it hasn't changed at all, we are suspicious that something is going wrong. But if it's changed by an unreasonable amount, then we also are suspicious of the measurement. So now if we have indication of a possible faulty sensor, sometimes through data reconciliation, we can provide a prediction of that measurement and be able to continue. But we spend a lot of effort on validating the data before we then send it to the emissions model. The emissions model then will be used to predict the actual emissions, and then it'll report to individuals to define reports that are required, data logs, and it also will provide deviation alerts and be able to send those alerts either to individuals or to groups that would be responsible for checking to see what happened. Next slide, please. Okay, now how do you deploy this? Well, this is software and it's very flexible. It can be installed on premises on a existing server or a new server, for example, and at level 2 or level 3 in the plant operating data system. If you have your own cloud, if the customer has a cloud, it can be installed in the cloud so that it's available throughout the corporation. Emerson has a cloud available too that we will be happy to provide to people if they want to use it. And it has software as a service also, which means that Emerson will maintain the application and the models. Now, if we have also a large number of these, we may want to look at something called a data lake, which is a particular type of a database which enables us to bring a lot of information together and be able to easily support distribution of this information to whoever might be interested in it throughout the corporation. Next slide, please. So in terms of the PEMS, there are 4 components. The first component, which we'll spend some time on, is the modeling and optimization component. That's what we use to analyze the data, recognize pattern, and then develop the models. Now, we want to be able to define actions on exceedance events. In other words, if we have a prediction that there is an emission exceedance, we want to have models that will tell us what to do with that information. Who should it go to? And what in this system is provided is the ability to do that using a graphical language. Now, the advantage of that is that if you have environmental engineers or other process engineers who may not be software specialists, they don't have to actually do any coding. They just have to bring the graphical tools together to enable them to predict this. And then the root cause analysis, which I mentioned before, which again, if there's an exceedance prediction, enables us to go back and find out what the cause of it might be. And then a workflow, which enables us to specify actions, either done automatically or done manually, and to check that those best practices are done in terms of equipment operation. Next slide. Okay, so a typical PEMS project evolves. First of all, there's the data acquisition for model training. Now, if you're going to have some predictions, you need to have some data to base the predictions on. And so this can be, for example, plant data that uses lab analysis or other specialized analyses that are done periodically in the plant of these desired emission checks. But more commonly is the fact that we'll bring in temporarily portable analyzers for the items we are going to predict, and we'll run test runs on the equipment to be able to make sure we've exercised it fully. Now, depending just on plant data gets us into the trap of the fact that often the plant data is over a very narrow range of operation. And so, when we're fitting the models to that range of operation, of course, that's where normal operation is. But we're not going to be very accurate as we deviate from where that data was taken. So bringing in portable analyzers and doing test runs is the most common way of providing this analysis. Now, actually, in the regulations for the U.S. use of PEMS, you need to do this on a periodic basis, about once a year, to bring in and check to make sure that your models are still predicting accurately. Then the second step, of course, is the model deployment, to put it out there, and then the development of the data acquisition and validation system, which we talked about previously. And then we test this now to make sure that it is predicting as we expect and matches the data. And then finally, we go through a deployment to actually put this on site. So this would be a typical PEMS project. Now, next slide, please. But again, as I said, there are different levels that we can use this software for. Now, one of them is to determining the cause of emission exceedance. So if we predict an exceedance event, then what we want to do is to be able to have the software help us predict what is the cause of the event and what action needs to be taken. So if we go to the next slide, this shows how this would work. And so again, move it forward one, and we should build on the slide. Yes, okay. So let's suppose we have an exceedance event. Do that again, please. It'll take us back then on the network of measurements that go into the system. And then one more time. And then one more time. And it will tell us what the root cause most likely is of the particular exceedance event that we're happening. Now, these are done for a lot of equipment. You don't have to develop this totally from scratch. There are pre-configured templates available. Next slide, please. So now, as I said, the next stage beyond that is to add in functionality that will enable us to predict and say how we should operate the plant to maintain it within emissions limits. And for example, as I said before, we might want to maximize production within emission limits. And so this would enable us to then be able to make the decisions about how the plant should be operated. Okay, the next slide. So a key part of this technology then is the modeling and optimization segment. Okay, and this involves looking at the data that we received and analyzing it. Now, if you look carefully at the picture, the drawing on the left, or the picture on the left, and you look in the upper left quadrant of that drawing, you'll see there are two dark areas and then a light area underneath. Okay, so what has happened is, through analysis of the data, we have been able to detect that there are two different modes of operation of the equipment. And so that tells us that when we're looking at the data for prediction, we need to check to see whether we need to develop models for the two different modes of operation, or whether we can just use one model over both of them. But this gives us an indication of how how the equipment's operating and whether we need to take its mode into consideration. Okay, and then in the center, then this shows the data analytics. So after we've done that and we've decided, how the data is to be analyzed, then we can take it into the data analysis and the AI machine learning algorithm. And so that data comes in, and then we're developing models. And then over on the right, if you look at that, if you're into statistics, you'll recognize regression and principal component analysis. And if you've worked with AI, you'll know neural models and such things as Bayesian analysis, random forests, and all of these are different kinds of AI analysis that you can use for building the model. And then that provides us then with these models. Now, this modeling tool is more general than just PEMS. It can be used to help us analyze other parts of the plant operation and look at, for example, can we have ways of detecting equipment problems? Are there things that can help us learn how to optimize better? And just look at that overall. So next slide, please. So in this, in the optimization side, if we've chosen that, then it provides what's called dynamic targeting. Now, this would be the case where we had a complex plant with multiple pieces of equipment. And so we needed to know what equipment is online or offline, or what equipment is being expected to be brought online. So we can use that then to decide about the potential operation of the plant to maximize production. It can also look at if there's special forecasts of different types of production, if there are other problems. In addition, it can go back in historical data and look at the best operation under different kinds of mode, and then be able to take that into the decision on what is the dynamic targets for the plant going forward. Next slide, please. And so again, I mentioned that this same technology can be used for adding reliability monitoring of equipment to PEMS. So this can increase availability. So being able to do this then enables us to look, for example, at compressors and pumps and other pieces of equipment, analyze their operation, and detect if there are precursor events that enable us to detect that there's going to be a problem with equipment going into the future. And this can take advantage of diagnostics that we have on the plant equipment. So in addition to emissions, we could get unit health and performance and be able to help determine the best way of operating the plant. Next slide, please. So what are the benefits of this? Okay, well, first of all, next slide, please. What we find most often is that capital costs of PEMS are about 50% of those of putting in a CEMS system. Now, those of you who have been working in this area know that very often if we're putting in a CEMS systems, the majority of the cost may be not in the analyzer itself, but if we have to put in an analyzer house and have to put in a sampling system with long runs, that can cost significantly more than the analyzer. Of course, that is not required if you have a CEMS system. Typically, of course, this is a much faster project implementation. Takes typically weeks rather than months to implement. In terms of the ongoing maintenance, it's typically much cheaper. Now, if you have a CEMS system, again, if you're familiar with this, you know that you have to calibrate the system regularly. And you also most typically have to make sure the sampling system is working properly. And so all of these things tend to mean that to achieve a 95% reliability on an online analyzer is sometimes difficult, okay? But with the software-based analyzer, it's typically 99.5% plus, okay? Also, it means that models can be easily updated as you have new information available or bring in new pieces of equipment. It's easy to replicate this across multiple pieces of equipment. Now, the two major sets of regulations that this will meet in the US, the CFR 40 parts that are listed there, and then the EU regulations which are listed there as well. Now, the U.S. and the European regulations vary a little bit, particularly around the requirements for retesting of the models on a periodic basis. So a couple other things. It's easy to replicate across multiple sites. So if you have multiple pieces of equipment that are similar, you can use the same type of models, and that reduces the work. If you have multiple sites, again, you can put it in. And if you have that, then you can facilitate centralized modeling and maintenance. For example, if you have this over several different plants, you can have one group that's centrally located that really focuses on maintaining all of the models and make sure that they're all up to date and working well. Okay, one more slide, please. Next slide.
No moving. Okay.
Okay, and then so we'll look at a case study here. Next slide. Okay, so this case study is on a system for an international floating LNG vessel. Okay, so this is based upon Emerson's analytics, and it meets the European regulations. The models include gas turbines, boilers, gas engines, flare, and a thermal oxidizer. And the composition predictions include, CO2, methane, carbon monoxide, nitrous oxide emissions, and sulfur oxide emissions. Okay, next slide. So this is an example of the displays that we received. This is an overview display. So again, next slide, please. So here we are looking at one of the boilers, and we're looking at the ability of the boiler, what it's producing. And you can see that it's predicting for this boiler the SOx and the NOx and the carbon monoxide and the carbon dioxide, and then providing a trend over the recent period. It's providing an indication if there was a problem, and then it's providing a graph of historical data. Next slide, please. And then if we want to see the total emissions from the site, our location, in this case, then we can look at that, and that will tell us what the total emissions are for all of these things, for CO2, carbon monoxide, NOx and SOx, and then also what's the historical data on that as well. Okay, one more slide, please. So this is another example. This is kind of interesting. This is an example of combining a CEMS system with a PEMS system. So this is a carbon black reactor. And for this reactor, you have to operate in the lean range with O2 so that it's slightly under the O2 required for complete combustion. And it's very difficult to maintain this. Now, you have to have enough oxygen, enough air coming in to maintain the combustion, but you want it to be really, as I said, lean. So you have to, and this is difficult because the feedstock qualities typically change. Now, the carbon black plants have very specific regulations and emissions reporting requirements. So in this case, in addition to the modeling, the controls were put in. And what was done, now there was an oxygen analyzer that was actually installed. And then the oxygen analyzer, in conjunction with the temperatures in the reactor, and of course the fuel gas flow, were used to predict carbon monoxide, carbon dioxide, and NOx in the tail gas flow. So this enabled us to have an improved carbon black yield, because if you put too much oxygen in the reactor, then you actually combust more of the carbon that you want to, and it comes out as CO2 rather than as carbon black. So this provided additional capacity and it improved the energy efficiency. And it helped us to be able to, the client to be able to meet the regulatory compliance reporting. So next slide, please. And then next. So if this, we look at this as part of a digital transformation in a plant. And this is the way we typically approach these digital transformation applications. First of all, an assessment based upon the digital maturity model of the plant. This is a Emerson model that helps us to kind of assess where you are. Then looking with the plant staff, both the operations and maintenance staff, in a collaborative format that enables us to get together on what are the important areas to be implemented in the plant. And then a roadmap of possible projects going forward with their potential payback. And then making sure that we have ongoing management to be able to implement the projects with regard to what is desired. And then finally, in the transformation, to be able to monitor the improvements to make sure that it's available. Next slide. So again, this might be a way of assessing a site with regard to its digital maturity and its ability to handle these kind of applications. And so this would involve then projects that could be implemented over a period of time and other things that would be advisable to make sure the plant is ready to maintain these applications. Next slide, please. And then this is built on a large portfolio that Emerson has developed around value improvement practices for plants in different areas through a digital transformation. So next slide, please. And then the next slide. So in summary, as we have said before, air quality regulations are not going away. They're going to continue to evolve and evolve in a more restrictive way. Making sure that we meet these regulations is a continuing issue the plant's going to have to deal with. If we can find emissions that we can handle with software rather than with physical analyzers, that's going to certainly save money in terms of operation. So these predictive emission systems can meet these requirements and meet the regulatory requirements, and also provide an overall improvement program that can be part of a digital improvement program, which is looking at not only this, but other ways that digital transformation can help the plant. Next slide, please. So if we go look at this in summary, some of the requirements for the software system should be that it's in a standard framework that's open and available. Again, we want this to be something that can be maintained going forward, that it has advanced models, that it can use hybrid modeling technology. By that, we mean normal statistical analysis, and then also AI-based type of applications as well. That it can be deployed on premises or off premises in the cloud as desired. That that it can provide root cause analysis. So if there is an exceedance event, it can help us to detect what the problems in the plant are. And then that it's open and it's easy to maintain and it's designed for low code or no code and provides graphical programming interfaces for implementation. And that it can handle large deployments on multiple pieces of equipment and multiple sites. One more slide, please. So again, I'm sure you guys are thinking about lunch. So this is a request. Emerson has 2 booths there, and they're located right across from the food. So it should be very easy to visit them as well. Okay, next slide, please. So thank you, and questions. We're glad to answer any questions or comments. And of course, again, if you want to just email me something, my email again is pretty simple, doug.white@emerson.com, and I'll be glad to respond to any questions as well.
Yep.
But any questions there?
So have you had scenarios where the output from this PEMS was significantly higher or lower than the actual emissions? If so, what are, I'll frame it this way. What are the scenarios where the PEMS output is going to be higher or lower than the actual emissions? What type of conditions can cause that?
Well, again, you're fitting the models to the data that is available, either test run data or historical data. So if the equipment moves into a new mode of operation, which you were not anticipating, then of course you're going to get a larger error. But the advantage is that if you determine that that is the case, you can redo the models and redo the checking and be able to update the models so it can handle the new situation.
But in the annual test, you talked about the annual verification, right? Have you had scenarios where the actuals came out very different than the PEMS output? During the annual
Well,
verification?
I mean, understand we're fitting the software to the data that's available. So it's by definition, the software is going to match the data. All right, and as long as as long as the plant is operating within the range that you've got data for, then you can expect your software to be pretty accurate. If you go outside that range, then then that's when you're going to have more issues.
Okay. Yeah. Thank you.
Other questions?
So kind of along the same lines about the stack test data, for the validation testing, is there regulatory requirements then to also provide that kind of reliability or validation of the data that's being fed to the model, the flow, temperature, pressure data?
The regulations are around how well the software matches the data. So in the case where you have where you bring in, so you develop the models, you're using it, then you bring in the test kit and run another test. And there are regulations on how well the software has to fit the model, or else you have to refit the software. So that's where the regulations are, but they don't define the internals of the software or the validation. But that's based on practice, on experience. That's where the problems come in. If you don't have the data validation, then if you get some type of a problem with a measurement, which might just be a piece of equipment shut down, then you're going to have a poor prediction.
So there's no restrictions even on the data reconciliation, like if one of those flow meters or pressure transmitters goes out, we could also kind of create a model for making up that data, and there's no regs to.
No, there's no regulations. The regulations are all around how well your software matches the data.
Thank you.
We have to use like data substitution. Some regulations call that out. So
Okay.
it might be driven by a different regulation.
Okay, understand.
Okay, other questions?
I think it's all,
Thank you, and I'm sure you guys want to go to lunch, so
thank
yes,
you very much, Doug.
Thank you.
Great, great, appreciate it.